All right. Today we're going to talk about a very special, very important section in robotics, that is manipulator dynamics. And this is also a document which is getting built, particularly dynamics on Lagrange Euler formulation. So let's see what this is. Contents of this document. Probably this will end up being a book or booklet rather uh, in the future, near future maybe. Now, first thing I want to present to you is Lagrange Euler dynamics. And of course, a lot of people are using Lagrange Euler dynamics and not many people know what it is, how it was derived and so on. So therefore, we need to look at what it is in the first place. First of all, dynamics is actually motion model. Okay, motions are due to forces and torques. And if you know how these are related, forces and torques, right, of a robot manipulator, causing its joints, its links to move. And if you can precisely write down the equations that will describe the following motion of each and every link, you have a mathematical model, dynamic model. To build that is the key point here. And you might be wondering, haven't we done that before? Yes, you have done it before using Newtonian laws, right? F equals ma is the first equation that comes to everybody's mind when we say dynamic equations, right? If there's an object and there's a force, imbalance force applied on it, the mass has to accelerate. And there's a very clear relationship equation, F equals ma. So when you write that down to a mass or system of masses collection, you have the equation that you can use to calculate the acceleration of the object and then everything else that follows, like velocity and position, etc. If it's a rotation kind of thing, of course Euler comes in, Euler's equations. It tells you if you give a rotational moment, we call it that way, the object has to turn at a certain angular speed versus the linear speed Newton explained, right? And you have the angular velocity and angular position like that, same way that you do much more conveniently in the linear motion, right? Now, the Newtonian mechanics is just one, right? There are other dynamic models. Now, if you go to very small particles like quantum physics, you cannot apply Newtonian mechanics. So it is quantum mechanics, okay? Slightly different. So sometimes you use forces, etc., to figure out the following motion, but you also can use energy to describe the motion, okay? Because energy is related to motion in some way, kinetic energy, energy due to velocity, okay? So therefore, there's more than one way to write down equations of motion, right? Now I think you understand, okay, there's a way to go beyond Newtonian. So therefore, let's look at this one, Lagrange Euler dynamics. Now what you see over here is this. This graph, you can see there's a motion from time t1 to t2 of an object, right? It starts from here and moves like that, and time t2, it's over here. And there's a force applied, and the force causes the motion. Qt is the variable that describes the motion, the position of that object, okay? Now, this is what is called the natural path. Like, for example, when a coconut drops from a tree, there's a natural path, right? It doesn't go here and there, right? It falls in a certain way. And if you just drop it, the plucker, just drop it, it comes vertically downward. But if the plucker gives a little moment initially, it will follow a projectile. So that is a natural path. So there's only one natural path. Okay, every time you do that, if the conditions are the same, it will follow the same identical path to the ground. And sometimes you can call this as the path of minimum action. The path of minimum action. The object doesn't take more than what it really requires to follow that path, minimum path, okay, or natural path. Now, when we as mathematicians, if we want to find out what is that natural path for an object, if it is subjected to imbalance forces, right? We need to have a way to find out, okay, what is the natural path, right? All of these dynamic models, Newton and Euler in this case, they're trying to find out this natural path, okay? Now, let us broaden our discussion. As you can see on the right-hand side photograph, this time you can see other than the natural path from T1 to T2, you draw few other paths around, possible paths, right? Possible paths. And then same endpoints at T1, T2, you have the same endpoints, right? But in between, you can have more than one path. So now collection of paths. Now we call this kind of thing a functional. And if you get just one path, say natural path, let's call it QT. As you can see on the left-hand side diagram, QT is the natural path, okay? Or minimum energy path, optimal path, right? You know it. And on the right-hand side, there are other paths slightly deviated from the natural path. We call them perturbed paths. There's some sort of perturbation, disturbance, some deviation from the natural path. There are so many of these paths, infinite number of paths. And if you combine all these things together, we call it functional. That you can see it over here. Q bar T is what is called a functional. Functional. Now we can declare the problem this way. Given the functional Q bar T, can you find out what is the optimal or minimum energy path, which is QT, the dash line like this. So this is an optimization process with respect to a set of functions. Now earlier classes, we have done optimization of a function, right? Looking at the rate of change. When the first derivative comes to 0, you get a peak, right? Or minima or maxima. You did that earlier. This is optimization of a single function. Now, this time, you take it one order above to find out which one of these functions is the optimal, the minimum effort path. Okay? And this is what is called in mathematics calculus of variations. Calculus of variations. All right? Okay. Now, I want to make it as easy as possible to you so that I want your 100% attention here. Every equation I'm going to show you, right? You need to write down on a piece of paper with a little note. Otherwise, I want to warn you upfront, this is going to blow your mind, right? It will be very, very difficult for you to come back and figure it out later if you do not get it right now. Now, this is how I write down the functional. Look at equation 1.1. Q bar T is the functional, right? All of the functions, collection of functions, right? Is equal to Qt, that is the natural path, plus epsilon st. This is how I write it, epsilon st. So st is a small distance along the path. and epsilon switches from one path to another, right? All of these paths are specified by some value in epsilon. Okay, when epsilon is 0, you are referring to the natural path. When epsilon is not 0, it is any other path that you can see over here as continuous lines. Okay, so this is the functional. And also I can say these two equations. What is that? Any function, all of the functions, right, in the functional at time t1 should be equal to qt1, the position of the natural path, because it's one single unique point at time t1 and also one single point, unique point at time t2 at the end. All of these functions will have to satisfy these 2 points. So therefore, at time t1, you can write down this equation, you can write down this equation as well. So q bar t1 is equal to qt1 plus epsilon st1, right? Now, if you want to satisfy the two boundary conditions, right? If you look at these two equations here, how can you satisfy this condition? Q of t1 plus epsilon st1 is equal to qt1. Of course, the epsilon st1 has to be 0. Okay, but you know that epsilon is not 0 for all the other functions, right? Except the natural part. So therefore, st1 has to be 0. So the st1 has to be 0. And along the same argument, you can also say st2, that is the small deviation at time t2, right, is equal to 0. So st1 is equal to st2, or s of t2 are 0. Okay. This is how we define the functional. We're talking about collection of functions between t1 and t2. They share the same 2 points, initial and end, and in between they are different to each other. Okay, so we move forward. Next thing we do in Lagrange Euler formulation. By the way, Lagrange is a famous French mathematician. He was like some 20-30 years junior to Euler, right? When Euler was like in his early 50s, Lagrange was like 20s. At that time, Euler was the mathematician of the world. Okay, and Lagrange was just a young mathematician, but he did not go to reputed universities, or he was not known as a famous mathematician back then, but he was very smart. He studied, he taught himself, something like that. Then he wrote to Euler, the mathematician of the world, his ideas, and Euler picked up very, very quickly. And he saw some bright ideas by this young mathematician. Then they started working together and revolutionized the world of mathematics. That is very interesting. In your leisure time, please read about Lagrange, okay, and Euler. Of course, when you start reading Lagrange, you will see Euler in almost all records. Okay, so Lagrange presented what is called Lagrangian. This is his idea. Okay, he said, let's define a function called L, symbol L, of time q and q dot. And this time it is q bar and q bar dot, because we are talking about all of the functions, right? The functional. as Ek minus Ep. Ek is the kinetic energy, Ep means potential energy. So in any system, you have the kinetic energy, you have the potential energy. All right. Think about very think about the famous control problem. You have gone through this problem. Everybody has gone through in the first course in controls. The mass spring damper system. Think about just mass spring system. There's a mass, there's a spring. And when the mass moves, there's an kinetic energy. And also when the spring squeezes, you store energy in the spring. That is potential energy. Okay. So the motion is because of this transition. How much of this energy is going from kinetic to potential, or back from potential to kinetic? Okay. This transition causes the motion. All right. So in that discussion, there's no force applied. Force means there's no Newton there. Okay. If you just think it like that. So Newton explained the same thing using a force. All right. When the spring squeezes, there's a force. There you go. So Newton picked up the problem in terms of force. But even without that, you can explain the motion if you can follow the energy transfer. Okay. So when potential energy transfers to kinetic energy, you get the speed, acceleration. All right. So there's no need of force there. Now, this is the Lagrangian. Remember that. Lagrangian is kinetic energy of the system minus potential energy of the system, right? I don't think it's a big deal to remember it that way. And we'll define what is called the augmented Lagrangian. Augmented Lagrangian, right? What is that? You can see in equation 1.3, capital A coming over here. Otherwise, it's the same thing. But the difference between 1.2 and 1.3 is this new term, Ft epsilon s of t, right? So Ft is the force, epsilon st is the slight deviation between these functions in the functional, right? So that is Lagrange, that is what Lagrange presented as the augmented Lagrangian. Okay, so augmented Lagrangian is bit confusing, I would say, but Lagrangian is straightforward. It's difference between kinetic and potential energies. In fact, kinetic energy minus potential energy. All right. Right. So the S here is a small distance, right? Very, very small distance along that path specified by epsilon, right? And there's a force, there's a small distance, there's a small work, right? Amount of work. So you add that also to the Lagrange, right? And then you have kinetic energy, potential energy, some change in these kinetic and potential energies because of that additional work, all right? So what's going to happen to this function, right, is actually what's going to happen to the motion of the system itself. So that is why they're so strongly related. We can find out a way to the motion, to describe the motion along these lines. Now, Lagrange says this. If you have the augmented Lagrangian, right, this one, and if you integrate from T1 to T2, you get some value. You get some value for each and every function from T1 to T2, right, including the optimum or natural path, right? But this integration from T1 to T2 is minimum for the natural path. That's what Lagrange said. In fact, it is zero, right? All the other paths is not zero. So if you minimize this integration, all of the functions, right, from T1 to T2 over the functions, that's what I said, find out the minimum action a minimum effort function of this functional, and that is QT, optimum path or natural path. Just like the path a coconut takes when you drop it from the tree, right? It comes along in a certain path. So that is QT, natural path. Okay. If you put a steel ball or something on a ramp and let it go, it rolls down, natural path. Okay. Doesn't go through any other path because it finds the optimum path naturally. So mathematically speaking, this is how you write it. You evaluate the integral from t1 to t2 over all of these functions and get the minimum value. Which function gives you the minimum value of the integral? And that is the optimum path. All right. So how do I find out? Find that optimum path? Well, in maths, I have figured out you want to differentiate the integral with respect to the function, right? Function, not time. It's not differentiation over time. Okay. You differentiate the function with respect to time if you want to find out the optimum point in time. At what point you get the optimum. Here it is not the case. We want to find out which one of these is the best minimum energy function or path. So therefore you have to differentiate this with respect to epsilon. So epsilon is the number that uniquely specify the path. Epsilon 0 means the natural path. We know it already. And all the other paths, there's some value for epsilon. So differentiate the integral with respect to the variable epsilon, right? So that is this equation 1.5. And of course, you know, once you get the integral and differentiate it with respect to epsilon, and then set epsilon equals 0, because we already know the natural path is when epsilon is 0. That is how you, when you get QT, the natural path, optimum path. Okay. All right. Then if you further move, also maybe this is something you need to know in maths. There's Leibniz integration rule. This is also going backwards to historical notes. Roughly along the same time Newton lived in UK, right? I think it's Germany or France. There's another mathematician lived by Leibniz. Okay. And some people say they invented calculus pretty much at the same time, but eventually Newton got the full credit as the inventor of calculus using his famous uh, book, Principia Mathematica. But Leibniz also did quite substantial work in calculus, but not a lot of people know about him. So Leibniz has this integration rule. So when you have the total differentiation or total differential of an integral, you can actually take the differential into the integral. So that's why we take this d over d epsilon into the integral and write it that way, 1.6. Okay. So this is Leibniz integration rule. Now, when we move forward, you can see the differentiation of the augmented Lagrangian with respect to epsilon. Now, when we start differentiating the augmented Lagrangian with respect to epsilon, we figure out that the Lagrangian is multivariable. It's not a single variable, right? It has time, it has q, and it has q dot. So how do you do differentiate a multivariable function? Of course, using partial derivatives. So that's why we have these partial derivatives, partial of the Lagrangian, right, uh, with respect to epsilon plus then the second term over here, right, ft epsilon st, right? So this is directly differentiable with respect to epsilon. So therefore, you don't need partial. You need partial only in the first term. Okay, so there you can see the partial differentiation in the first term, and the second term is total differential d over d epsilon. In fact, when you do that, it will become ft because epsilon goes out. But the Lagrangian, this one, you have to work out the partial differentiation. Okay, so this is how we do that. Uh, in fact, here we can write down d over d epsilon, and later we introduce partial, right? Okay, so this is partial of L with respect to Q bar and partial of Q bar with respect to epsilon, the chain rule of differentiation. In every multivariable function, this is how you differentiate, okay? Not just one differentiation, but two. First, you get the partial derivative of the function with respect to one of its variables, and then that variable with respect to epsilon. Next, you have to do the same thing for Q dot. It is partial of L with respect to Q dot. Q mean actually Q bar here. And then Q bar dot with respect to epsilon. Okay. So it goes like that. Now, if you look at how the functional is defined, you can find out expressions for this one, partial Q bar over partial epsilon, as well as here, partial Q bar dot over partial epsilon, right? Where should we look at? Let's go up to the functional, right? Over here, yeah, over here. And if you want to partially differentiate, right, this one with respect to epsilon, right, and Q dot, when you differentiate this Q dot, Q bar dot, then Q dot, and um, S dot, right, like that, you get expressions for these two, this one and this one. Okay, so the first one, partial of Q bar with respect to partial epsilon, is just ST differentiation. And then you differentiate Q bar expression, and with respect to first you differentiate with respect to time to get Q bar to Q bar dot, and then partially differentiate with respect to epsilon and to get this one. Okay, so ST goes here to the first term here, second term here, and the second term here, for the second term here, goes S dot T. So you can write down this equation. All right. Any questions up to now? So I request you to do this one yourself, right? Write down the expression for the functional. Can show it to you again. This one, differentiate with respect to time to get another equation, and both equations you differentiate with respect to epsilon partial, right? So that'll give you these two expressions, st here and s dot t here. Okay, so when you set epsilon to 0 in this expression, right, you are getting the optimum path. Now, here the second term, if you look at this one, I can see that these are two functions, right? These are two functions. partial of L with this over partial Q bar dot, and then S dot T. So take these two, this term, entire term, middle term here, and I can say that this complies with the uh, this expression that we are familiar with in calculus, um, the um, the differentiation of a product or integration by parts, right? Either way. So have you now, do you remember this one, that integration of u dv is equal to uv minus integration v du? I think this is high school mathematics. Everybody remembers this one, right? So if you have to integrate a function u and a derivative of another function dv, right? This is the way you do that. You get the two functions u and v and put the limits minus integration v du, the opposite of these two, right? And that is the result. So if you get the second term over here, you have partial L, partial Q dot, and the other one is S dot T. So you can identify this part as U, right? And S dot T as dV for derivative of that function V. Okay, figure that out. So this is U, this is dV. Now, if you put into this one, it is equal to uv minus integration v du. So this is uv, the two functions, partial L, partial Q dot times st. These are the two functions. Put the limits minus integration. Differentiate the first one. This is dA by L over dA by Q dot. You differentiate it with respect to time times the second function, that is st. That is integration. Okay. Now, when you substitute the limits t1 and t2 for this one, st, it becomes st1, s of t1 minus s of t2, right? And of course, this part is 0 because earlier we said that in the definition of the functional, the two ends, right? All of the functions in the functional, they have to share the two unique points at the start as well as at the end, right? So therefore, s of t1, s of t2 are 0. So therefore, this 0 minus 0, we get rid of the entire function here. What we are remaining with is only this term, second term, right? So this is for the second term in this expression, this one, right? Why we do that? Because first term we have some st, third term we have st, second term we have s dot t. So we want to get rid of this s dot t in the middle term and substitute it with another term where we have st. And of course, here we found it. This is the second term. It is equal to this, where you have st as part of that. Okay, so when you substitute this expression minus this whole thing, right? For the second or middle term of the equation, you get this equation. You get this equation, all right? Now, can you see the st common here and here and here? So st comes out of the bracket, and for the natural path, epsilon is equal to 0. Equation 1.11. So for this integral to be 0, right? For this condition to be satisfied, because it's an integration, okay? St is not 0, right? It is 0 only at the t1 and t2, but in between, it's not zero. So therefore, how can you make sure, how can you give the perfect assurance that this integral is zero, is by saying that for every t, this has to be zero. Okay, what you see on the bracket has to be zero at all times. So this is what we can generally understand, because energy cannot be created or destroyed. Energy should be manifested in some form of potential energy or kinetic energy, right? It cannot have an excess amount or deficit. You can't have that, right? It has to add up to zero at all times, right? If energy, kinetic energy goes up, potential energy has to reduce the same amount, right? It has to be balanced at all times. You can't have energy at one point and give it to take at one point and give it some other time. Naturally, in a system, it doesn't happen. Okay. So therefore, at all times, at all t, the the expression in the within the bracket has to be zero. That is equation 1.12. So we put the condition equals zero for all times, right? Then Ft is the force acting on the system, right? This Ft, and L is the Lagrange, which is kinetic energy minus potential energy, right? Q is the variable, path variable, okay? If it's a linear motion, you can say it's distance. If it's rotary motion, it's an angle, okay? Right. And this force can be force or torque. If it's a rotary motion, it's torque, right? It's a linear motion, it's force. Now, if you want to balance the two sides without saying equal to zero, and you put external force applied on the system as Ft, what you can do is to arrange it this way, like in equation 1.14. What is that? The differentiation of partial derivative of L with respect to Q dot minus partial of L with respect to partial Q is equal to Ft. So this is like F equals ma in Newtonian mechanics, but this is different. This is what is called Lagrange-Euler uh, dynamics. Okay, maybe you have seen this for the first time, but accept it as another equation that you can put side by side with F equals ma. Okay, and if you want to find out the equation of motion of a system, now you have second option. You don't have to always look at Newtonian mechanics, F equals ma. You can use this one. So you might be wondering, how can I do that? Because this looks very intimidating, right? But it's pretty straightforward. You have to find out L. L is the kinetic energy minus potential energy. You can find out these expressions and differentiate with respect to the variable, actually the rate of change of variable, Q dot. You can do that. And then differentiate with respect to time. And then look at the second term, kinetic energy minus potential energy, differentiate with respect to the variable. And set is equal to the force applied. So you have equation of motion that way. Any questions? Have you been able to follow everything up to now? Yes or no? Tamira, is it clear to you or is it not clear?
So clear.
It's clear, right? What about others? Banuka?
It's clear, so but I think I had to go through this once again, the other things, but partially clear. Clear.
All right. Sulochana?
Clear, sir.
Sulochana, sorry about that. All right. So I know that you have to digest a little bit, right? But if you are confident, that's enough for now. But make sure you all make this document available to you this evening. You can download and read it and make sure you understand everything. Okay. Right. Now, to further reinforce your confidence, let's work out a little example. So this example is very easy and very familiar to you. You have dealt with this example earlier, right? So what is that? Figure 1.2 shows a mass subjected to gravity and an upward force, F. So what is uh, the situation you are in? Well, this is the situation. There's an object in a float, and there's a force upward, and there's gravity downward, and there's imbalance force, F minus mg. And we measure the distance from the vertical upwards, right? This x is the variable here. Okay, so if the force is higher than the gravity, it moves up. If it is otherwise, other way around, it falls down, right? So, if I ask you to derive the equation of motion of this object, right? This is what you do, right? You use Newton in mechanics, Newton in dynamics, right? The equation of motion of the mass is described as follows. Straight away, you write mx double dot is equal to F minus mg. Right? So mechanized to your thinking, right? You can straight away write the equation of motion. How do you do that? Uh, it says imbalance force. What is the imbalance force? F minus mg is one hand, one part of the equation, one side of the equation. The other side is mass times acceleration, mx double dot, right? Even with closed eyes, you can write it down, right? And when you rearrange it, you can write it like that, mx double dot, the highest derivative of the variable on far left, plus mg is equal to f, right? Or else you can say mx double dot is equal to f minus mg, whatever form. It's pretty straightforward that this is the equation of motion. So you have second derivative of x, right? If you know your initial point, what is the value of x right now, and you can use the forces applied, F and mg, and calculate x double dot at that moment of time, time zero. And time zero, there's an acceleration. You can integrate the acceleration, right? And find out the velocity and the distance, and you can go on and simulate what's going to happen to the object. Okay, right. Now, if I ask you to do the same thing with Lagrange Euler, what we have derived right now, you start with the Lagrangian. First, you have defined the Lagrangian. Lagrangian is kinetic energy minus potential energy, K minus P. So what is the kinetic energy of the object? Of course, it is half mv square. V means velocity, and here it is x dot. So it is half mx dot square. That is kinetic energy. So what is the potential energy? Going up and down, right? So it is mgx. You start x0, and if you go 1 meter, it is mg. 2 meters, 3 meters, like that, mgx. That is the potential energy. So you have the expression. This is your Lagrangian. It's very pretty simple in this case. Once you have the Lagrangian, right, you have to derive this. You have to build this equation. This is the equation of motion, and this is the Euler-Lagrange dynamics. Now you have L, differentiate with respect to the rate of change of the variable, that is x dot, and then differentiate with respect to time, right? So let's do that. Lagrangian differentiate with respect to x dot, right? We don't have the second term coming in because there's no x dot here. There. The first term has x dot square, so it becomes what? Mx dot, all right? So this is one should differentiate with respect to x dot. Then you differentiate with respect to time, then this x dot becomes x dot, x double dot. Fine. Equation 1.17. The second term of the Lagrangian, right, is Lagrange Euler dynamics is the partial of Lagrangian with respect to Q. So here Q is X. This is Lagrangian partial differentiated with respect to X. So look at over here. First term is not contributing because it doesn't have X. Second term has X. Differentiate with respect to X. You are remaining with mg minus mg. Now you have the equation 117 and 118. Combine them together into your Lagrange Euler dynamics. Mx double dot minus minus plus mg is equal to F. Isn't this the same equation that you have had got with Newtonian? Yes, it is. Now this is pretty convincing that you have more than one way to derive the system dynamics. Any questions? Okay. So, so far we have dealt with single variable systems. But if you look at a robot manipulator, let's say 6-link manipulator, 6-joint manipulator, there are 6 joints, 6 variables, right? So we have to be able to handle all these 6 joints, 6 variables as a single system. Okay. So in uh, Lagrange Euler case, it's pretty built into the system. So all what you need to do is to change the x variable here, and earlier it is variable q for the path, right, to a vector, single variable scalar into a vector. So you can write down the same equation, right, with vectors now. So in that case, x becomes x1, x2 up to xn, right, and the forces become a force vector, not just one force, there are so many forces. In a robot manipulator of 6 links, you have 6 motors and they generate 6 torques. So this is a torque vector that goes in to the manipulator. Okay. So F changes, F represent actually not just the force or torque as applicable. All right. So like that. Okay. In fact, I will change this X to Q because in well, I can keep it as X. But when we turn to robot manipulators, we don't use X for the joint variables, we use Q, all right? Yeah. So this is the vector case, vector representation of Lagrange Euler dynamics. There you are. Now we want to look at manipulator dynamics, okay? We already derived the Lagrange Euler dynamics. We know what it is. We know the equation, right? Now let's look at how we can apply that on manipulators. So as I said earlier, in manipulators, the joint variable vector is Q, generalized coordinates, and it has first variable Q1, Q2, up to Qn, all right? And this is an example robot manipulator, right? To make life easy, I use this planar manipulator. The manipulator is on the plane of the screen, right? We have the first joint, second joint, and the third one is a prismatic joint, linear joint, and eventually the last joint Qn. Okay, there's a torque generated by the first joint here, tau 1, and there's a torque generated by the second motor there, tau 2, and this linear joint, there's a force generated by that motor, F3. It goes like that. Some of the actuating um, uh, forces are actually not forces, they're torques, right? Some are forces, like that. Okay, and the other thing I want to tell you is that this is generally applicable to any manipulator, even though I'm using a planar manipulator. for convenience, right? Now, the Lagrange-Euler dynamics can be written to a manipulator this way, where the right-hand side force is changed to torque vector, because you have more rotary joints than prismatic joints in typically almost all manipulators in the world, right? So therefore, we use it as torque vector on the right-hand side. Still, there's a possibility that some of the forces in this vector, torque vector, are not actually torque forces, right? So I think you can handle that one. And the other thing is Q coming in place of X, all right? Right. So how can we build the Lagrange-Euler dynamic model for a robot manipulator? First, we need to find out the ingredients. It's like you are going to cook a food, a dish, and you want to get the ingredients, right, around you. Otherwise, you can't cook, right? You need to have all the ingredients ready. So what are the ingredients you need here? Of course, you know you have the Lagrangian, that is kinetic energy, potential energy, like that. So then if you look at deep down, what is kinetic energy? What is potential energy, right? Kinetic energy comes from the velocities, all right? So you need to have velocities, right? Like V, I. It's a multi-link manipulator. So every link you need to have the velocity, right? So if you have the link like that, right, as at the center, there's a velocity, right? So this velocity, this link is moving with that velocity. So in that case, you can say the energy, kinetic energy of the link is half m mass of the link times the velocity square. That's how you calculate the linear velocity, the linear kinetic energy because of linear motion. And of course, you have the rotary motion. In that case, you need to get the angular velocity and the inertia, okay? Same as the linear motion. So we have to do this homework and assemble the kinetic energy expression in this case. Right. So I think you remember the last lectures, we did the differential kinematics, right, for a manipulator, right? V is equal to Jacobian times Q dot. Remember, Q dot is the joint velocity vector, all of the joints. And then in front of that, you have the Jacobian, right? And on the left-hand side is the linear speed, velocity. So we can use this equation here as well, right? So to calculate the velocities, what is the velocity of each and every link? In fact, this is the linear velocity of the center of the link, all right? Then what is the Jacobian? Well, we still don't know, but we know how to get that using forward kinematics. So you write down the forward kinematics, differentiate, and try to assemble the velocity on the left-hand side, linear velocity, joint velocity on the right-hand side. In the middle, you find out the Jacobian, right? So we are not there yet. We haven't done it for this particular case, but we know how to get there. We have the plan. I think you guys should be pretty clear about it. We can do this. We have done it before in forward kinematics, differential kinematics. It's just a matter of using that over here. Right. So this is for linear velocity. So let me show you how these linear velocities are assigned. You can see the first link over here, right? Middle of the link. Can you see it over here? RC1. RC1 is the vector from the origin, that is O here, right? Origin of the first frame, x0, y0. You can see the coordinate frame here, x0 and y0. With respect to the point O, okay, the vector of the first link, RC1. And there you have V1, linear velocity, right? And if you look at the second link that comes over here, right in the middle of that link, right, you have the vector, that is RC2. And there's linear velocity V2. So every link, you find the center of the link, center of mass. The vector to that point from the origin is required, and also the velocity at that point, linear velocity at that point, is also required. Okay. And the kinetic energy comes from angular velocity also, not just because it's moving, but it's rotating as well. So what is the equation for that one? Well, first of all, the angular velocity of the link, that is omega, is equal to j omega I q dot. What is that? This is also differential kinematics. When you write down the differential kinematics for position, right? Like over here, right? This is for the position x, y, z. Then you get the Jacobian, linear velocity Jacobian. But if you write down the forward kinematics for the orientation, right? Roll picture, and then differentiate it to angular speed, you get this expression. Where on the left hand side you have the angular motion of the link, the rotation, right? And on the right hand side, q dot, joint velocity vector, q1 dot, q2 dot, and so on. And in the middle, you have the Jacobian. So again, I'm telling this to you. The path we have to follow is pretty clear. You have to write down the forward kinematics and then differentiate. Figure out the position part, figure out the orientation part. Our position part, when you differentiate, we'll get to velocity Jacobian, linear velocity Jacobian, and the orientation, when you differentiate, will lead to um, um, uh, rotation motion, right? Rotational Jacobian, that is j omega I. For each and every link, you can do that. Okay, so linear velocity Jacobian and angular velocity Jacobian, coming from the forward kinematics. Of course, forward kinematics, once you differentiate, becomes differential kinematics. There you can find out position part and orientation part separately. There's one Jacobian there, one Jacobian here. Linear velocity Jacobian, angular velocity Jacobian. We'll do a little example, then you will know the entire process. But at the moment, I want you to be like clear about the process. Okay. Right. So then uh, kinetic energy of the end link manipulator, right? Right. So first, let's look at the kinetic energy because of the linear motion. So I write it as K subscript L, the kinetic energy due to the linear motion. And of course, everybody knows the energy of an object which is linearly moving is half m velocity square, one single object. If you have multiple objects, right, all of these objects are moving at certain speeds, you write down the velocity as a vector. First element, second element, third, fourth as a vector. So in that case, this is how you write down the kinetic energy, right? Vi transpose times Vi. So velocity 1, velocity 2, velocity 3 as a row, velocity 1, velocity 2, velocity 3 as a column. When you multiply, you get velocity 1 square plus velocity 2 square plus velocity 3 square. And in front, you can have mi, the mass of the first link, mass of the second link, mass of the third link. Done. So as a single summation, this is the kinetic energy of a multi-body system, right? Like a robot manipulator with n number of links. Pretty straightforward. Then what about the angular speed and the energy because of the rotation, right? Because the rotation. Well, the rotational kinetic energy is given by this equation. That is angular speed, inertia, and angular speed. In fact, as everybody knows, it is inertia times angular speed square. Okay, inertia times angular speed square. But that is only for one single object. If you have n number of objects, like we have here, you have to put it like matrices and vectors. Okay, this is how you do that. So when you write it like that, the inertia matrix is in the middle, and omega I is the angular speed vector as a row, and omega I is as a vector. So then those things multiply in the proper order. Okay, when you deal with multiple bodies, like a robot manipulator here, and every link has a linear velocity and angular velocity, you definitely need vectors and matrices to write the combined energy, right, in very efficient way. Now this I of I is the inertia of the ith link with respect to the zeroth or base coordinate frame. And remember that all the motions are with respect to the base coordinate frame. Okay, from the base, if you have a link farther outward from the base, right, that's inertia of that one is huge, because the manipulator will have to work little more to drive that one, right? More energy is required than where all the other links which are close to the base, assuming same angular speed. Okay, so this inertia thing is a relative thing. It's not actually specific to uh, the, the link. We call it principal inertia, but in this case, every inertia is with respect to the base coordinate frame. Okay, because when you deal with energy, you have to look at the distance as well. So if you are given, let's say, a link, one of the links, right, of the manipulator like this pen, right? So you can you know the equations to write down the inertia along this longitudinal axis, vertical axis, right, and the lateral axis. Equations are pretty simple. But those inertias are principal inertias, right? But if I want to calculate the inertia with respect to another coordinate frame in this room, somewhere the corner, right? Then you need to do this one. What is that? I is equal to this one. Ri, then I. This is the inertia, principal inertia basically. Inertia of the link with respect to its own coordinate frame times Ri transpose. So it changes depending on the reference coordinate frame. So what you can initially calculate, if I give you a cylindrical or whatever shape rod, is this one in the middle. It is the inertia with respect to its own coordinate frame that you can calculate. It's a unique thing. It doesn't change. For a given link, it's constant. But if that link is in different points in space, right, it's going to create different inertias when you get the inertia described with respect to the base coordinate frame. So you have to calculate it time to time, right? When there's a motion, inertia is changing. Okay, so that's why we need to have rotation matrix. There you are. We have done rotation matrix earlier, and you can bring that to the discussion here. Okay, right. So the total kinetic energy is therefore the combination of these two, 1.24 and 1.25. So I put them together I'm building the equation for kinetic energy. And at the same time, I look at the different ingredients I need to have around me if I really want to implement this. And of course, by now, I have no problems. I know how to get the velocities, angular and linear, and also how to get the inertia calculated. Okay, right. Any questions up to now? Now look at this equation 1.26, right? This is a kinetic energy, combination of linear motion and angular motion. Now here I substitute for that equation, say this velocity, linear velocity. I have the equation earlier. This one, linear velocity, is given by this equation. The Jacobian times joint rate. So what I do is I replace this VI with that expression, Jacobian times Q dot, and here transpose and without transpose. So I get two of them, J times Q dot, J times Q dot. First one with the transpose. So now I don't have the linear velocity, but I have the substitution of that in terms of Q dot. Okay. What about the second term? Well, I need to have omega for that one. So where do I get omega from? I get it from this equation. Omega comes in terms of Q dot now. Now I'm replacing V and omega and I'm bringing in the Jacobians and Q dot into the discussion. So now you can see it is Jacobian Q dot transpose Jacobian Q dot. Very clear. And in the middle, II. So this II is actually rotation matrix times principal inertia times rotation matrix transpose. That is also not a big deal. So once you simplify these ones, right, see what's happening here. I work out the transpose here. J Q dot transpose is, you swap the two together, right? Q dot comes to the front, Jacobian goes to the end, right? And then they both have transposes, right? That's how you get the transpose into a bracket. Both of these terms, J and Q dot, get the transpose, but they swap the position. I think this is an identity in linear algebra. You may have done it at some point. And here also the same. They are also Jacobian and Q dot swap together. And we get this equation. And we look at very carefully, you can see a pattern. Look at the first term over here. There you can see Q dot transpose and Q dot, right? On the front and at the end. And the second term, same. Q dot transpose and Q dot. Okay? Can you see that? Both these terms, in front, they have Q dot transpose, at the end, Q dot. So then we can write this again in this format. You can take Q dot transpose to the front, out of the bracket, and also you can take Q dot out of the bracket like that. And then combine the remaining terms in the middle, the two terms in the middle, like this, right? When you do this one, this becomes n by n matrix. If you have 6-link manipulator, this is 6 by 6 matrix that you are building, okay? Right. So if you look at Q dot transpose and Q dot over here, right, you can take that out of the summation this way in equation 128, right, leaving the summation only up to this point. Then in the next line 129, you can see half Q dot transpose is remaining there, right? And q dot at the end is also remaining there. And the entire summation here, n by n matrix, right? I can give you a symbol for that, q or d of q, this big D matrix, right? The mass matrix of the system. So it has masses and inertia and the Jacobians, right? Some matrix. For a given manipulator, you can actually find that out for a given position. When the position changes, matrix also change. And a matrix is a collection of elements. Okay, it's a two-dimensional matrix, so it has rows and columns. Rows defined by say I, columns defined by j. So each row, each column can be modeled using two summations. Say summation I from 1 to n, and then summation j from 1 to n, right? This is how you span a rectangular array of elements, right? This is another way of writing down the D matrix. In that case, uh, this q dot transpose and q dot at the end, you don't need to have them, right? This entire thing is a set of numbers, right? Calculated or defined by these two summations, right? And of course, every term need to have two q dots because these are vectors. Q dot is a vector. It's a q1 dot, q2 dot, q3 dot, like that. So when you multiply them together, right, row vector and column vector, you get all of these combinations: q1 dot, q1 dot, q1 dot, q2 dot, q1 dot, q3 dot, like that. All of these combinations are there. Okay. So 1.30 is the final expression for the kinetic energy of a manipulator. Now, I want to tell you this. What is the nature of this DQ matrix? The DQ matrix is a symmetric matrix. Why? If you look at the way it has been found, you can see it is q dot transpose q dot front and at the end, right? So in linear algebra, we know that a matrix derived as A equals B transpose B is symmetric, right? If you have same matrix transpose and then without the transpose, you multiply them together, resulting matrix is symmetric. That's one case. The other one is a matrix derived as A equals B transpose CB, where C is symmetric, is also symmetric. So you have a matrix which is a symmetric matrix in the middle, and in front you have some matrix transpose, and at the end you have the same matrix without the transpose. When you multiply and get the result, it's also symmetric. So here, this is what we have, right? If you look at these ones, these are all symmetric matrices, right? And then this is q dot transpose q dot. So therefore, the resulting matrix q of D of q is symmetric. So this is very important because if we know that this matrix is symmetric, when you want to calculate these terms, you only need to calculate half of the terms. The other half you already know because it is symmetric. Okay, this is a serious advantage. All right, I think it's time to take a little break over here. Any questions, please? We have completed the process of getting the kinetic energy expression, right, of the Lagrangian. Any quick questions, please? All right, in that case, let's pause for a break of 10 minutes. All right. So now we have the equation for the kinetic energy 1.30 or 1.29. Let's look at how we can form the potential energy, right? Now, this is the potential energy of the manipulator. It is G transpose RCM MI. R is the vector of the center of mass of each link is 3 coordinate vector x, y, z. You need to get actually the height. Okay, in our case, height is actually the y coordinate. If you look at this one, y coordinate with actually y0, right? The base coordinate frame, which is our reference frame. All of these vectors RC1, RC2, etc. are with respect to the base coordinate frame, and it has 3 coordinates x, y, z. We want to get the y coordinate. And also the gravity works downward, negative y0 direction, but we don't have to worry about negative y direction. We just need to multiply the y coordinate of the RC vector, RC1, 2, 3 like that, with 9.8. Basically, that's what you want to do. And also with the mass of that link, right? You know the potential energy of a link is mass times gravity times height. Height is y coordinate. So you can easily build that expression here this way, right? When you deal with 3 coordinate vectors, all of these things are 3 coordinate vectors except m, of course. Gravity, let's define like this: 9.80. The second term is 9.8. That's what we want. And RCI is also 3 coordinate vector x, y, z. We want to take y. So second term is the height here. That's why we put 9.8 in the middle term here. Okay. So with the potential energy expression written like that, 1.30, now you can combine the kinetic energy you wrote earlier together with the potential energy you created now, put them together and form 1.32. This is the Lagrangian kinetic energy minus potential energy. Now the next step is partially differentiate the Lagrangian with respect to q dot. So when you do that, you can see the second term doesn't have any q dots, so it goes off as 0. The differentiation partially, right, with respect to q dot is only operational in the first term. So you can write down it like this. Second term is 0. To figure that out, to make life a bit easier, let us take just one joint variable, that is q dot k, right? So you have 6 of these, right? Let us take just one, index k. So how do you do that? As you can see it over here on the right hand side, it is partial of this expression with respect to q dot k, right? How do you do that? Shall we think about two-link manipulator initially, right? Just two links, right? If you have just two links, you can expand this double summation here manually without much trouble. So I equals 1 to 2, j equals 1 to 2. So when you do that, right, you will see D11, right, D12, D21, D22 appearing, right, for I and j. Can you see that? 4 terms, these 4 terms that you can see over here. Okay. And middle 2 terms are the same, D12, D21, because we know these are symmetric, right? D matrix is symmetric. So therefore D12 is equal to D21. Okay. So you can combine the middle 2 terms together to this one, and it's just 3 terms now, right? And this is for uh, this is actually the second term. Now, if you differentiate this uh, with respect to 1, joint 1, right? You get Q1 dot. This one differentiated with respect to Q1 dot. What do you get? You get this one, right? And if you differentiate with respect to Q2, you get another one, right? If you had n number of links, right, process is the same. So you can write down the differentiation in this summation format, j equals 1 to 2, dij qij, right? That's what you get for the first term. Now, if you generalize this for kth joint, that is partial differentiation of the Lagrangian with respect to q dot k, right? You will see that this number 1 will change to k. That's it, right? dkj q dot j, this summation, right? So what we have done right now is that we have taken the Lagrangian and try to differentiate with respect to um, q dot, right? And we found out that 1.34 here will describe this in case of two link manipulator, right? So link 1, link 2, you can write it like that. Now the next thing is you want to differentiate 1.30 with respect to time, right? So when you do that, you can see it over here, right? This comes as two parts, dkj q dot j, two terms, right? So when you differentiate this like a product uv and you differentiate like udv plus vdu, right? You keep say dkj constant and differentiate q dot j, first term, it becomes q double dot j. Second term, you keep q dot j constant like that, differentiate djk with respect to time. All right. So this expands into two terms. So this is for a two-link manipulator. Remember that, okay? For a two-link manipulator. So then what do we do next? The first term remains as it is, right? Q double dot. You can see the joint acceleration coming into the picture now. And the second term, how do you do the differentiation? dkj, right? Differentiate with respect to time. Now the problem is dkj has joint variables, right? Like q1, q2, both. In this case, it is uh, uh, two-link manipulator, right? For n-link manipulator, it has n number of joint coordinates. So therefore, you cannot differentiate. Of course, you have to differentiate with respect to, you have to take partial differentiation, right here. So that's why this partial dkj or partial qi comes in with qi dot. For each and every joint variable, you have to do this. So in addition to that, you have this q dot j out of the brackets. Okay. So why we do that? Because dkj, these d components, they are formed by joint variables, right? You have n number of joint variables, so you have to differentiate partially, right? Now, when you combine these two together, you can say it's double summation again. All of these variables dk, kj, we have to differentiate partially with respect to qi, and I goes from 1 to n. And after that, you have to multiply with j, qij, right, for all of the variables, 1.35. So this is the first part. This is the first part of the Lagrangian, Lagrange Euler dynamics. Can see it over here, d over dt, partial of Lagrangian with respect to q dot. What about the second term? The second term is developed by taking partial derivative of L, Lagrangian, with respect to qk, right? Now look at that. That differentiate with respect to each and every joint variable. If you have n number of joint variables, n expressions, right? So if you go back to the Lagrangian, right? This is the Lagrangian. Now you have to differentiate this entire term with respect to qk, right? Joint each and every joint variable, right? So 1.32. When you do that, you get this one, 1.36. You can see partial differentiation of dij with respect to dk, right? This is what you want to do. And also you have to multiply with qi dot j, qi, q dot j, q dot I coming in. And also the second term is the potential energy. This is connected with joint variable q, so therefore you have to differentiate partially as well. That is also there, 1.36. Now 1.35 and 1.36 are the two expressions we need here. One is the kinetic energy, the other one is the potential energy. Now we have to combine these two together. 1.35 minus 1.36 is equal to the force, external force. Here we have a manipulator, and external forces are actually the torques generated by the joint motors. Right, so this is the Lagrange Euler dynamics. Now we have to put the two equations over here. The first one 1.35, second one 1.36. So this minus this, right? That is this line over here. I know there's no way for you to remember 1.35, 1.36, and when you put together, you get this one. But what I want you to do here is that to find out the progression, right? How we are going from one step to the other. Later, you will get this one tonight. You can download and study yourself. Okay. Now, if you look at the left-hand side, this is the joint accelerations. You can see over here, joint accelerations, q double dot. Joint velocities here, right? And joint positions are here in djk. These terms, joint position is there. In addition to that, the masses and everything is there. This is the dynamic model. What's remaining to be done is to simplify this a little bit. How can we do that? Let's look at the first part. J equals 1 to n dkj q double dot j. This is the acceleration times the mass matrix. Okay. Part. Just leave it as it is. And the second term here, the double summation, and the third term is also a double summation. We can combine these two together because they have a lot in common. You can see that one. Q dot I, Q dot J. Here also the same, q dot I, q dot j. So you can combine these two terms in the middle together, like over here. Okay? And the third term comes over here. Partial of P with respect to a partial with respect to joint variable qk. So I'm writing this for qk, just one um, joint, just one joint. And on the right hand side it is tau k. That is the torque of that joint, just one. So when I change this k to 1, 2, 3, 4, 5, 6, I get all of them. Okay. Now equation 1.37 is very interesting because there we write down the expression within the bracket in the middle term in a very elegant way. You can see that the expression is actually uh, partial dkj over partial qi minus half of partial dij over partial qk. This one is written in this format, right? What is that? Half partial dkj over partial qy plus half partial dki over partial qj minus half partial dij over partial qk. Now the pattern is this. Every term here has half and it is plus and minus. And if you look at just one term, numerator and denominator, when it is dkj, the denominator is I. When the numerator is ki, the denominator is j. When the numerator is ij, the denominator is k. Can you see? This is swapping numerator subscripts and denominator subscripts in a very elegant manner. Now, because we want to simplify this, we define this entire term in the long bracket with the three terms, each get a half in front of that. This entire expression is actually called Cijk, C subscript ijk. Okay, and is the summation. So it's very compact form now. And Cijk should be remembered as this. Okay, and Cijk is what is called the Christoffel symbols of first kind. Remember that word? I think in the book it's somewhere there. Christoffel symbols. And it tells you this coupling between different joints. Joint 1 is connected with joint 3. Joint 2 is connected with joint 5. Joint 1 is connected with joint 3. Like that. All of these coupled dynamics and the forces and moments, right? How they actually cause motion is actually captured in this coupled format here. So finally, we have this dynamic model up to this level developed, right? So 1.38. Now, what follows from this line over here is that if you look at this one over here, this double summation partial dkj over partial qi, right, uh, can be written half dkj over qi plus half uh, partial dki over qj. So this one, right, this is for the first term over here. This term over here, right? The first term within the bracket here without the half, of course, this is actually written using this expression with two terms with half in each. Okay, and put it over here. Then all these three terms will have half in front, right? This is if you want to find out whether this is true or not, one test is, okay, let's put I and j equals 1 and 2, right? For again, two-link manipulator, I and j are both equals to 2, right? Sorry, I is 1 and 2, j is 1 and 2, right? Like that. So then you can write it down this way: j equals 1 to 2, I equals 1 to 2, partial dkj over partial qi. Write it down. So when you write it down, you will see the left hand side, j equals 1 to 2. When I is substituted here, it is dkj over partial q1, then this partial q2, because I changes from 1 to 2. And then you put j equals 1 and 2, you generate these four terms. On the right hand side, also do the same, right? First put I equals 1 to 2, you generate four terms, these two becomes four terms. And then put j equals 1 and 2, you generate 8 terms. Right? On the left hand side, only 4 terms, right hand side, 8 terms. Okay? Because left hand side is just one term here initially, and right hand side you have two terms initially. So these two terms become 8 terms, this one term becomes 4 terms in the double summation. Now these 8 terms on the right hand side here are actually, there are similar terms. How can I find out? Say the k1 over q1. Look at the first two terms here. They are similar. You can add them together, right? So therefore, these 8 terms is actually 4 terms. And the 4 terms are equal to these 4 terms. Okay? So that is why we say that this term here on the left hand side can be written as this term on the right hand side using two terms, and each got half in front. So that's why this expression becomes this expression, right? With 3 terms, and all of the terms have half in front. Okay, so that is for Christoffel symbols. So this is the expression for Christoffel symbols, right? There's a pattern, half, 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 plus and minus. This is kj over I, ki over j, ij over k, right? Now, with the Christoffel symbols, this is the Lagrange-Euler dynamics of the manipulator for any joint k from 1 to n. The middle term is very interesting, right? The middle term is very interesting. So we want to pay with more attention to the second term here. So let's take the second term and try to expand it. Okay, that's what we are going to do here. Under centripetal and Coriolis forces, title. All right, so this is the second term, double summation, Christoffel symbols, qi dot qj dot. Let's write it down for a two-link manipulator to make life easy. So j equals 1 to 2, I equals 1 to 2. And this is the expression you got, right? 8 terms. Right? So first one is for k equals 1. Right? Now we have two joints. So first joint, right? K equals 1, you get 4 terms. And k equals 2, you get another 4 terms. Right? So like that. Now, if you look at these 8 terms, you will see that some of the terms, they have these dots of the same joint acceleration. For example, the first term, Q1 dot Q1 dot. So this is Q1 dot square. And also the last term here, you can see Q dot 2, Q dot 2. This is second join Q dot 2 square. So you can get the square terms combined together as the first term, right? And the other terms as the second term in a matrix form, where Q1 dot and Q2 dots are combined together, right? So when you look at this expression 1.40, what comes to your mind is that, okay, I have seen this before, right? The first part on the right hand side here is Q1 dot square, Q2 dot square. And this, what is this? This is what is called the centrifugal terms, or the opposite one is centripetal force, right? When you swing an arm like that, right, it goes out. There's an outward force, and to avoid that, you need to pull it down inwards, right? So there should be some sort of force inwards, right, from to keep it from moving outward. So that force is what is called centripetal force. Okay. So your robot will have this centripetal force in order to move it like that. So the first term here will tell you what is your centripetal force. Second one is what is called the Coriolis force. Coriolis force. So the Coriolis force comes with Q1 dot one velocity with Q2 dot another velocity. When you have two velocities combined together, right, there is a force generated which is called the Coriolis force. For example, these days you see not in Sri Lanka but in Hong Kong and in US, Florida, there are typhoons, cyclones, right? They start from the tropical belt near the equator, little above the equator, and they start moving upwards. Okay, moving upwards. So as they go northernward, right, you expect it to go straight up to the North Pole, let's say, whatever direction it's heading, right? But what actually happens is that it turns to the right, to the eastward. This is because of two vectors, two velocities. One velocity is its own velocity upward to, say, north direction. The other one is the rotation of the Earth moving eastward, right? This velocity and that velocity, when they combine together, it gets the Coriolis force. And the Coriolis force is this one. And that is why, right, the cyclone, the epicenter, when it moves, it always curves eastward, right? And sometimes because of that, it doesn't make the landfall, right, as expected. Tangentially brushes or touches the land and then again go back to the sea. So in every mechanism where multiple links are moving in different directions, you have the combined Coriolis forces. Right. For two-link manipulator, you can describe it this way. But for n-link manipulator, same process, right? Because it becomes more massive, more labor. That's it. But again, what I can tell you is that in MATLAB, you have symbolic math, the differentiation, etc. You don't have to do manually. You can write code and MATLAB will do it for you. Right. So you have the centripetal forces, you have the Coriolis forces, right? This is for the second term. When you break the second term into two terms, you can figure that out. All right. So, right. So, now the final term, we don't have to do anything at this moment until we get to a specific problem. Just leave it as it is. That is the potential energy and its differentiation. Where do I find it? Maybe I can scroll further up. Um, all right, fine. Maybe I can bring you again back to say 1.38. Let's say this one, right? So the first term is basically like what you have seen in Newtonian mechanics, F equals ma, the acceleration times the mass is the force, right? So look at the first one. Can you see something similar there? Yes, of course. So this is qj double dot. So every joint in the manipulator, there's an acceleration. So in order to accelerate a link like that, rotary motion, you need to generate a torque, right? So for each and every link, there is this inertial torque, and that is the first term over here. Okay, that's fine. Then you have the second term here with the Christoffel symbols. And just a while ago, we have broken it down into two terms. One is when you rotate something, right, it tries to move outward, and prevent it from going outward, you need to push it inwards also. And therefore, you need to generate another force. Okay, so that is embedded in the second term. And also when this joint is has a certain velocity, the other one is has another velocity, the two velocities coupled together, it generates a Coriolis force. And that is also embedded in here. Okay. And this one is the potential energy differentiated with respect to uh, Q, the joint angle. So I think we have touched all of these terms qualitative, not um, in detail implementation or not yet in numerical format, right? Just the understanding of what it is. All right. So when you put everything together, we can write down the dynamic equation of the manipulator in this symbolic format: dq q double dot cq q dot times q dot, and g of q is equal to uh, the joint torque vector symbolically. Right now, this is not a surprise to you anymore. You know what these elements are. Okay, this is the mass matrix dq, all the inertial torques, and cq dot is the um, Christoffel symbols, and it represent centripetal and the Coriolis forces, and this is the potential energy differentiated with respect to joint angle. Now I want to spend a little more time on Christoffel symbols. This is something new to you. You might get confused if you do not understand it at this moment. And understanding Christoffel symbols is also not that easy. But spending a little more time will help. Right. So according to the definition of the Christoffel symbols, Cijk, if I pedal back, right, uh, this is Cij definition. Okay, Christoffel symbol is three partial derivatives, right, of the items in the mass matrix. Their partial derivatives with respect to joint angles. Okay, so if you write down C1111, you get this one. And of course, there are a lot of similarities here, right? T11 over Q1, D11 over Q1, D1 over Q1 cancel out, remaining just one of them. This is C111. Okay. But what about C211? So then it looks like this. It is half D11 over Q2. What about C121? Well, it's like this. It's equal to C211. One you have calculated earlier. C221 is like this. 112 is like this. 212 like this. 122 is like this. And 222 is like this. For a two-link manipulator, you have eight of these. Eight of these. Think about a three-link manipulator. When you have three of these, I, J, K goes from 1 to 3, 3 times 3 times 3, 27. You get 27 Christopher symbols there for three-link manipulator. But the good news is that is is automated, right? Just the labor. There's nothing complicated than that. Now you can understand that whatever is happening to link J has an effect on link I. Okay, in some form, is in Coriolis forces, they are connected in some way. And we cannot just forget it, right? We have to take that into account if you need to have a very clear dynamic model, right? To say exactly what forces and torques you need to drive a manipulator, right? Accordingly. So simple models can be used to drive, but then you generate errors in the process. To recover from errors, you have the control design, right? To catch up and eliminate the errors on the go. That's fine. That is the purpose of designing control systems. But if you really want to have a very good idea about the forces and torques involved or required for a manipulator to move it from A to B along a certain trajectory, you got to understand what are the detailed relationships of the manipulator. Okay, so for that we are trying to understand or dissect the manipulator deep down and figure out what it is. All right, so remember, for a two-link manipulator there are 8 Christopher symbols. That is 2 times 2 times 2, and for a three-link manipulator it is 3 times 3 times 3, 27, and so on. Okay, I think now it's time to work out an example. So when you work out an example only, you develop your skills to actually implement what you have studied. Okay. So for that, I use this two-link manipulator again, right? You can see that one is a planar manipulator, Q1 and Q2. I have two links. This is RC1, the center of gravity of the first link, and this is RC2 at this point is the center of gravity of the second link. Okay, and you see the two velocities v1 and v2, joint angles q1, q2. Okay, in fact I can see um, uh, the coordinate frame assignment here is actually the modified DH convention or the Craig convention, but I switched from Craig to standard DH representation recently to avoid confusion, to make it more consistent. So therefore, this X1, Y1, right, frame should appear at the end over here, right? I will make that correction before I release this to you, right? And also you can see here I1, this is the principal inertia of link 1, and I2, principal inertia of the second link. All right. Now we need rotation matrices to actually describe the inertia of the two links with respect to frame 0. Okay. So this is uh, the first link with respect to link 0, the base, right? It's just a rotation by this angle q1. Okay. just a single rotation around Z axis. And if you look at the second frame here, right, it's at the top of the end of the link, not here, right? Um, it's a rotation around a Z axis by two angles, right? Q1 and Q2 both. So we know how to write the rotation matrix for a rotation around Z axis by a certain angle, right? So it is this one, the basic rotation around Z axis. This is R2, second frame. You have two angles, Q1, Q2, and written like that. Rotation matrix are there. So in any manipulator, if you know the arm configuration, you can write down the rotation matrix. We're gonna need inertia matrices. Okay, so how to do that? Of the two links. Let's assume let's say thin rods, right, as our links. Okay. In fact, this is true for most of the manipulators. Manipulators are designed this way to get rid of some of these complications in dynamic modeling. So if you get a cylindrical rod as your links, right, you can write down these principal inertia. You can see around x-axis, around y and z axis, around the center of gravity, right? These are the principal inertias, right? Along the axis is almost zero. Along the axis, because it's thin rods, inertia along the axis of the rod is zero. We assume it to be zero. Around the other two axes, at the center of gravity, midpoint is mass times length square times 12. Okay. So with these three principal inertias, right? One is zero, the other two are equal. You can write down IC1 and IC2. That is the inertia at the center of the link. Link 1, link 2, right? So this is all right. But if you want to calculate the inertia with respect to the base, right? The first link has this one, R1 times I1, 1 I1 times R1 transpose. In fact, this IC1 is 1 I1. Okay, so like here you can see this IC2 is actually 2I2. The inertia of I2 with respect to its on frame. Okay, so you can actually find out the expression for I1 like this. This is I1, 1.46. And also you can find the expression for I2 using this one, 1.47. So 1.46, 1.47. All what you need to know is the inertia, principal inertia, and also joint angles, two angles, Q1 and Q2. Okay. Moving forward, we gonna need linear velocity Jacobian. Remember, I was telling you, these are some certain things you need to know. I have to combine these things together, and then you can apply them on the Lagrange-Euler dynamics. Now, if you look at the first link, the center of gravity, let's call it x1, y1, z1. These are the equations. You can write down the forward dynamics, forward kinematic equations, right? Half L1 cos q1 for x, half L1 sine q1, that is for y, is at d0 because this is a planar manipulator on the plane. It doesn't have anything out or into the board, right? Into the screen. So Z is 0. What about the second link? Well, it is L1 cos Q1 plus half L2 cos Q1 plus Q2. See, this is just the trigonometry. So what is the y coordinate of the second link, center of gravity? It is L1 sine Q1 plus half L2 sine Q1 plus Q2. So this is forward kinematics. Now let's differentiate these equations and then you get these equations. Once you differentiate, then put them into matrix format, combine the first three equations on the left hand side as x1 dot, y1 dot and z1 dot. On the right hand side, you have q1 dot, q2 dot, joint speed. On the left hand side, Cartesian speed. And in the middle, this is the linear velocity Jacobian. You need that in your dynamic model. For the second link, same. You have the Cartesian speed on the left hand side, joint speeds on the right hand side, and in the middle you have the joint velocity Jacobian for the second link. Okay, so these are the Jacobians with respect to the base coordinate frame. Everything is with respect to the base coordinate frame. Because you write the forward kinematics with respect to the base coordinate frame. Okay, all right. What about the angular velocity Jacobian? Well, there you can say your angular velocity of the first link is actually this one, right? Omega 1 is simply q1 dot. Omega 1 is q1 dot. What about omega 2? That is q1 dot plus q2 dot, because whatever angular speed of the first link, right, is assumed by the second link as well, because the second link also moves with the first link. But in addition to that, second link generates its own angular velocity as well. That is q2 dot. And you have to add that together. Okay. So I'm assuming both of these joints are rotary. Now, if you look at these two equations, you can figure out the angular velocity Jacobian. So this is the angular velocity Jacobian of the first link, and this is the angular velocity Jacobian of the second link. All right, so we know that as well. Now, when you have the linear velocity Jacobians, angular velocity Jacobians, like we did earlier, we can now combine these things together to form the uh, the mass matrix, right? And we found it earlier in 1.28, 1.29. I don't want to go back. So when you put them to the energy equation, right, Lagrangian and differentiate, you get this one, right? So this is the mass matrix D of Q, summation from I equals 1 to N, this expression, right? So now substitute for mass, linear velocity Jacobian, Cartesian velocity Jacobian, and the rotation matrices. We already derived all of these things, right? And just substitute. So this is the substitution. It's a long process, but just labor again, right? Don't have to worry too much about it. But I recommend you write it down yourself at least once so that you know what it is. You will remember it for a long time. Right? That is a long expression, all matrices, but eventually you can generate this one, 1.53. This is the mass matrix or inertia matrix of the manipulator. Can you see that? M1, M2, these are the two masses of the two links, L1, L2, and you can see Q1, Q2, the joint angles, they're all there. So this D matrix, inertia matrix or mass matrix, right, has actually four terms. It's 4 by 4, 2 by 2 matrix. But we have seen earlier that this is a symmetric matrix, right? Theoretically, we proved that. Now, practically, we also see that. You can see this element that is 1 2 element is equal to 2 1 element. This one, they are equal. Okay, so it's a symmetric matrix. And also, if you look at the first term here, this is the total inertia of the first link, the total inertia on the first link, the first joint. See, m1 L1 square over 3, this is the total inertia, right, of the first link, plus this is the second link, M2. Inertia of the second link is also felt by the first joint, because everything that is connected to the manipulator, right, are felt by the joint one. It's like mother. All of these inertias are felt by joint one. Okay. And this is the second joint, right? It only feels its own inertia. Can you see that? M2 L2 square over 3. This is two link manipulator, 1 and 2. The second one feels its own inertia only. So these are the three terms in the mass matrix. So when you have the inertial matrix, the mass matrix multiplied by q double dot like that, you generate the dq q dot term. This is the first term in the mathematical model, Lagrange-Euler dynamic model. Okay, so you have done the first term. Congratulations. Right. So this is a quite substantial thing for today. Right. You first time got to see uh, the inertial torques required uh, at the joints, joint 1 and joint 2 in this case, two-link manipulator. Right? This is not all, but the significant part of the dynamic model. Now let's move on to the second term, where you have Christoffel symbols. So for two-link manipulator, we have 8 Christoffel symbols, and these are the Christoffel symbols. We have already derived it earlier. The first one, right, D11 over Q1, because this is D11, first term in the D matrix. You differentiate it with respect to Q1, the answer is 0, because there's no Q1 there. What about C211? This is the expression for C211, Christoffel symbol. Take D11, the first term over here, differentiate with respect to Q2. Well, there's Q2 here, so therefore it is not 0. This is the answer. What about C121? C121 is equal to C211. We saw it earlier, so therefore it's going to be the same expression. All right. What about C221? C221 is this expression, bit longer than the others. So you have to differentiate D12, which is this one, with respect to Q2. So you can see Q2 in here, so therefore it's not 0, right? It's going to be like this. What about C112? C112 is equal to partial of D21. D21 is over here, right? This one, 212, right? With respect to Q1. So there's no Q1 here. Therefore, the answer is 0. So likewise, you can take each and every Christoffel symbol here and find out the partial derivative, and then look at your D matrix here, find out that particular D component and differentiate with respect to that particular Q with the expression over here. So once you do that, all of these 8 Christoffel symbols, you can combine them into this format, right? The first four Christoffel symbols are associated with the centrifugal or centripetal rather forces, torques, and the other 4 Christoffel symbols are associated with the Coriolis torques. Okay. Now with all of these terms known to us, and you have how many zeros? 1, 2, 3, 4, 5 zeros. Right? You have only 3 non-zero terms. So you can write it like that. Okay. So 1.57 is the Christoffel symbols. Finally, the third term is the torques and forces due to gravity. Torques and forces due to gravity. So for that, we need to get RC1 and RC2. Of course, we know these two values, right? RC1 is the center point of the link 1, that is L1 by 2 cos Q1, L1 by 2 sin Q1. And the second link, center of gravity, is like this. So we know RC1, we know RC2. With the reverse gravity vector, that is 0, G0, remember, gravity is working downward, but our Y is upwards. So if you want to have a positive number for G, you need to have a reverse gravity vector. So this is G transpose RC1 M1, G transpose RC2 M2. The total potential energy as one expression comes like this. Okay. Now, potential energy is not a vector, it's just a scalar, right? Just number. And then you differentiate with respect to Q1 and Q2, the two joint variables, 2 degree of freedom manipulator. And then you generate a column vector, 1.6. Okay, right. Here, this Q1 plus 2 means Q1 plus Q2. Okay, this is a shorthand notation. So now you have generated your initial terms, Coriolis and centripetal forces, and then the gravity torques, all of them, right? In this dynamic model, where, let me scroll up and show it to you. Just one expression. Where is that? I think before this, yeah, this one. This is the Lagrange-Euler dynamics. Three terms on the left-hand side. The first one is the initial terms, like Newtonian force equals m times acceleration. And then the second term is the Coriolis terms, which represent centripetal forces and Coriolis forces. And then the third term is the gravity. Okay, right. So now in this example of two-link manipulator, we have got all these three terms, and now we can combine them together. Okay. So the total Lagrange-Euler dynamic model of the two-link manipulator is just this, right? The first term times Q double dots plus the Coriolis and centripetal forces plus the gravity terms. On the right-hand side, torque 1, torque 2, because two-link manipulator, you have two torques. Right. Now, I will do the little edits of the note and upload it tonight up to this page 20, right? I need you to go through this document before the next class, because it is extremely important that you understand Christoffel symbols, inertial terms, gravity terms, right? And come with a complete understanding for a simulation next time, right? Because I want to do a MATLAB simulation so that you can understand how it works, right? Any questions, please? The other terms I don't want to take today. Once you study everything, I can expand it from page 21 onwards. Any questions, please? Chaturanga, how is it? Can you catch it up, or did you understand, or was it very difficult? Chaturanga, are you there? Mahindaratna, are you there?
Yes, sir.
How is it? Have you been able to follow it?
Yes, sir. Yes, I think it is successful. Anyway, I will go through the document again to that means to reorganize the points and
All
to
right.
refresh.
All right. Sulochana, how about you?
Yes, sir, got the idea, but I need to go through the document once again.
All right. So that's the purpose today. Banuka? There's a noise from your side.
Can you hear me now?
There's a big noise coming from Banuka.
Hello, sir, can you hear me now? Hello?
We can hear you, but there's a noise coming from your
Oh, yeah.
mic.
Yeah. But it's clear for me also. But I have to go through this once again.
Yeah, maybe Banuka can check his mic again. Until he does that, how about the others? Samira? Samira, are you there?
Yes, sir. Need to read it again and understood and some
All right.
things.
Okay. So that's the whole purpose. I don't expect you to fully understand the content we discussed today because I know it's a bit complicated, right? You have double summations, matrices. Uh, so uh, I'll upload the document before the day off, and I request you to go through it line by line and write it down yourself and come prepared for the next class. So there we will more consolidate on the Lagrange Euler dynamics, and we'll also walk through a MATLAB exercise so that you can see the manipulator in motion, right? So really convincing about the theory. All right. So with that, I want to wind up the session today. Then I'll see you. Yeah. Any questions,
So,
please?
is my mic clear now?
Yeah. Now it's clear, Bhanuka. Yeah, go ahead.
Sir, there's a small question about the assignment 3, sir. So, what exactly are we expected from the assignment 3? Is it like, do we have to like do it manually or in mathematically, or like do we have to like derive it in MATLAB?
What is assignment 3, by the way?
It's about dynamics. The dynamics
Uh,
assignment, yeah.
That's
Trajectory.
kinematic modeling, sir. Dynamics.
Yeah.